Here's a single mathematical result written in two ways. On the left, the way a person writes it in a paper, and on the right, the way it's written in Lean, which is a formal language that a computer can check step by step. To us, these are plainly the same theorem, but to a computer, they're completely unrelated strings. If you take a step back, there are two distinct sets of these types of results. There are millions of results that have been written by people in papers, and a smaller, fast-growing body of formal mathematics written in Lean, which is the language that much of today's AI for math is written in. Today, about only 1,600 of these links exist, from informal to formal mathematics, and every single one was drawn by hand, using blueprints. But because informal math predates formal math, we find that the same result gets proved in both worlds again and again. There are far more links between these two corpora that stay hidden because annotations only extend so far. So here's the question that drives this work. Can we find these missing links at scale? If we do it, we get a map of what's already been proven, and with Lean at the statement level, we can see the math it formalizes. Every result in math sits in a web of others. To prove one thing, you often have to lean on simpler results that came before it. These arrows and relationships together form a large dependency graph. The two main ones we've described and the ones we use in this paper are informal math and formal math. Informal math is everything you see in papers, and we've parsed nearly 12 million such results. It's vast, but it's written in prose where a subtle error can hide for years. The second such world is formal math, written in Lean. You can think of a proof as a chain of dominoes. Every single step must fall, or the computer stops you at the exact broken one. Nothing can hide from the compiler the same way it might hide in prose. The problem is, the formal side only covers a sliver of the math we know so far. These are the two worlds drawn side by side, to give you a picture of how they might look in relation to each other. Before we can drive the rich connections between them, we have to map each one individually. To build the informal graph, we take the source of every paper in the math archive and pull out its numbered results. These are definitions, lemmas, and theorems that make up the results of the paper. Here's one, straight from the page, a symmetry group that gets defined. Every definition, lemma, or theorem becomes a fact, and subsequently a node in this larger graph. Now we populate the links between these nodes. First, and most immediately, the author's own pointers, latex references, show that inside theorem 4.1, we have a direct resolution to lemma 3.2. The second type of link is called a prose queue, which has no command at all. Just by seeing the words, by theorem 3.1, the author references this theorem inside of lemma 3.2. Our parser spots the phrase and draws the link. Third, and the last type of link, is called shared notation. The symbol omega appears here inside theorem 3.1, but it was defined back in definition 2.1, which is a clear hint that a language model can use to tie the two together. But an important question is whether or not the links actually check out. An independent judge, Kimi 2.5, audited 500 of these papers, and the clearer the signal, the more it verifies. Author pointers are almost always correct, but they recover the fewest edges. The language model recovers the most, although fewer than half hold up under verification. Combined, 68% of all edges are verified through this process. If we repeat this process of building out a paper into its graph across all of Math Archive, the literature nets 11.75 million facts that get joined by 18 million links, and every link is one of these three kinds. On the other hand, the formal graph is much easier to parse. In Lean code, many of the dependencies are immediately visible. A theorem is literally built from the names of what it depends on, so when we read the dependencies, it comes straight from the code. Across 25 projects, we find that we get 388,000 total results. The problem is that Lean code and paper prose don't look anything alike, even when they say the exact same theorem. So before we can compare them, we need to express a shared medium. We make that medium by asking one instruction model to describe each side in plain words, using no mathematical notation. As a result, a slogan is produced, which is a short, intuitive description of what the statement is saying. It's not the theorem itself, it's like an approximation, but it gives both worlds the same kind of sentence to compare. Doing this for every fact on both sides nets 12 million in total. Once a slogan exists for every fact, we can turn its slogan into an embedding. A model called Quen3 reads the slogan and returns a list of about 4,000 numbers, or a point in space that tries to approximate the meaning of that sentence or phrase. A good way to think of embeddings is like an address in a meaning space. If two slogans are saying similar things, the model gives them nearby addresses. And so, the coordinates are not arbitrary in this case. Moving around the space changes the meaning. A classic toy example is man, woman, king, and queen forming a parallelogram across two axes. The arrow from man to woman points almost the same way as the arrow from king to queen. Roughly, we have a gender direction. It's an idealization, but the point holds. The location in this space carries some sort of semantic information. This becomes the glue of our system. When the embedding of a lean statement slogan and the embedding of an informal statement slogan are this close, it means they're saying very nearly the same thing. This in turn becomes a strong candidate, such that these two statements might be saying the same thing, which is exactly what we're looking for in terms of a match. Then we take all 12 million of these embeddings, formal in blue and informal in red, into one shared index. This becomes just one big bucket of points, and nothing is explicitly linked to anything yet. A direct comparison would mean that every formal fact against every informal fact would net 4.5 trillion checks in total. That's the wall here, scale. To get around the wall, we use an HNSW index. It's like a layered map of the embedding space, sparse at the top and denser as you go down. Query starts at the sparse top layer. It hops to the nearest looking neighbor, keeps the best option as seen, and only drops down when the current layer can no longer improve it. By the bottom, it has searched a tiny neighborhood instead of 11 million statements. With ANN sub k set to 50, the best neighbor is our Euler match at cosine 0.94. The pairing we get back is called a candidate pair. A formal side and an informal side, each with its code or statement and its slogan. This is laid out as one row, read from left to right. We repeat this search process for every formal fact. We fire a query from each one, and just over half, 55%, find a candidate through this process. Repeating the search gives us a distribution of candidate similarities, from roughly 0.5 up to 1. A score near the top means that the slogans are nearly identical, but cosine is still only a lead. To choose the cutoff, we sample candidates from each similarity bin and ask whether they are real matches. Below 0.8, the yield drops fast, just 23% in the 0.7 bin and 2% in the 0.6 bin. As a result, we set 0.8 to be the floor. Above it, we keep about 100,000 candidate pairs in a table: formal statement, informal statement, and cosine similarity. This table is what gets sent to judging. But in reality, a slogan is just a compression. To see why that can be dangerous, look at a simpler analogy where two sentences sound almost the same, but mean totally different things. Here's the first sentence. Everyone loves somebody. For every person, they love at least one other person. Now, if you swap the order of the two quantifiers, it becomes, somebody is loved by everybody. These are almost the same words and almost the same slogan, but a completely different claim altogether. A slogan can blur these two together because it's only an approximation, so the next step cannot trust the slogan alone. The judge gets the full lean statement and the full archive statement before it decides. The judge we use is called GPT 5.4. For every candidate pair, it reads the whole record, both slogans, the lean signature, and the original archive statement. It doesn't see the cosine score and no graph context, just the mathematics. Then it rules, exact, inexact, or wrong, and explains its judgment in a single line. A verdict is one of three. Exact means the two results are saying the same thing without any caveats. Inexact means the two results are the same, but up to a caveat. It may be a generalization, a special case, or only hold in one direction. Wrong, on the other hand, is meant to catch ideas that have shared words but don't express the same results at all. And so, we judge all 100,000 candidates using this process. The verdict splits like this. We have a small core of exact matches, a large band of inexact ones, and the rest marked as wrong. We treat exact and inexact together as matches, and we find that across 100,000 candidate pairs, our judge affirms around 48%. In the very top tier, almost 90% hold up. But a lingering question is whether or not the judge is right. We gave a human expert the same candidates blind, without them ever seeing the judge's verdict, and we compare what they said. Here the expert said that both are the natural number form of Bertrand's postulate, which is an easy, clear match. Here he says that the paper means a unitary map, which in turn forces orthonormal bases, which is context that the judge wasn't given. As a result, this is an exact match. On this one, he says that mathlibs is the internal covering number, while the papers is external. A closer formal match definitely exists, hence this is inexact. Re-ran, the judge agrees with itself at a kappa of 0.86, and with the expert 8 times out of 10. This is a strong, calibrated proxy, but it doesn't serve as good ground truth, considering that the sample size was so small. However, it gives us a basis to understand which models work best for this type of judging, and helped us calibrate GPT 5.4 to start. In the intro, and in our first toy example, we try to draw one line between an informal and a formal statement, but now we have shown at scale that there are thousands of these types of connections. As a result of our research, we're releasing all of our work. The dataset, the tools, an open API, and a plugin that any AI can call. The last visual we show is the two worlds of mathematics finally united into one map. We present Theorem Graph, made by the UW Math AI Lab. Thank you for watching, I hope you learned something new. If you have any questions, please comment in the thread below.